Life cycle assessment, also called LCA, is a method of evaluating the environmental effects throughout a product's entire existence, examining each phase from the extraction of raw materials to manufacturing processes, consumer usage patterns, and final disposal methods. By examining each stage, LCA helps people understand how a product affects the environment over its entire lifespan. It provides insight into the hidden costs of production and consumption that, while not always visible in a product's price tag, contribute significantly to resource depletion and pollution. Human ability to see the larger picture through LCA allows for making informed decisions about design and consumption. A powerful example of life cycle assessment can be seen in the smartphone industry's supply chain. LCA reveals how the mining of rare earth minerals in various countries creates acid mine drainage and habitat destruction, while manufacturing processes in other nations consume massive amounts of water and energy. The global transportation network connecting these phases adds carbon emissions, and short device lifespans coupled with difficult-to-recycle designs create mountains of e-waste. By mapping these interconnected impacts across borders and ecosystems, LCA shows how the impact of the technological systems people use extend far beyond individual consumer choices, exposing the need for systemic changes in how products are designed, manufactured, used, and recovered. LCA connects closely with the broader realm of sustainable design, highlighting how materials and production methods can be optimized to minimize negative impacts. It also relates to environmental policies, as many laws now require companies to disclose the life cycle impacts of their products. Furthermore, with the increasing amount of electronic waste, LCA is a critical tool in information technology for designing more environmentally friendly devices and recycling processes. These connections demonstrate how LCA can inform and improve practices across different fields, leading to more thoughtful and informed approaches to meeting human needs while protecting natural systems. Life cycle assessment is especially relevant when considering industrial 3D printing systems. Every stage, from extracting petroleum for plastic filaments or mining metal powders, to manufacturing the printers themselves with their precision components, to the energy-intensive printing process, to handling waste materials and eventually disposing of obsolete equipment, affects the environment. By evaluating these stages, engineers and designers play an important role in reducing harmful impacts. For example, they can focus on creating closed-loop material systems, where failed prints and support structures are recycled directly into new filament on-site, dramatically reducing both material waste and transportation impacts. This shift not only minimizes resource consumption, but also creates new possibilities for localized, on-demand manufacturing that reduces global shipping. Life cycle assessment provides valuable information to people and organizations who care about integrating environmental considerations into computing practices. First, through LCA, developers can design 3D printing systems that minimize material waste through optimized slicing algorithms and support structures. Second, LCA helps material scientists create biodegradable or recyclable printing materials that reduce end-of-life impacts while maintaining necessary performance properties. Third, in the realm of distributed manufacturing, LCA contributes to designing systems that produce goods closer to where they're needed, reducing transportation emissions and packaging waste. Together, these approaches show how technology can take into account long-term environmental best interests and help people keep the planet healthy while advancing human well-being.